Debargha Mukherjee. I'm a principal engineer at Google, and we worked on AV1 in Google between 2015 and 2018. The core engineering team included myself, then names such as Yao Shu, then Jingning Han, Zoe Liu, who is currently a co-founder in Vision Nuller.
Yeah, really excited for the conversation. And, maybe I know I kind of know the history, but I always like to hear it from those who are actually there rather than second and third hand. What is the history of AV1? Tell us how the standard even came to exist.
Yeah, so you know that there was a company called Onto Technologies that was acquired by Google in 2010, and at that time Onto had a codec called VP8. So the first thing that was done by Google at the time was take VP8 as is and make it an open source royalty-free codec. So that was the birth of the WebM project, and it started off with VP8. And VP8, as you may know, is still being used in many real-time video applications all over the world. So then, right after VP8 was released, then we started working on VP9, and the goal was to release VP9 at the same time as HEVC around 2012 or 2013, around that time frame. So which we did. So VP9 kind of was competing with HEVC, and it turned out to be working pretty well. And YouTube then decided to use VP9, started streaming VP9 in 2013 onwards, and slowly over the next 2 or 3 years, the adoption of VP8, VP9. I mean, the number of videos that were available in VP9 that were being consumed daily grew to billions a day, just because YouTube was streaming VP9. So on the back of the success of VP9, then what happened was we started looking at VP10, a further generation from VP9. But at the same time, there was a lot of interest in this project from many other companies that also have a big presence in online video delivery, such as Netflix, Amazon, then Facebook, and so on. And Microsoft. So what we decided at that time was, instead of doing VP10 as part of the WebM project, to create an industry consortium. So those negotiations started in 2015, and by the end of 2015, what was born was an industry consortium called AOM, or Alliance for Open Media. Okay, so, and then it was decided that VP10 would no longer be released, but instead, whatever you have done in VP10 would be proposed for this AOM codec, and the first AOM codec was supposed to be named AV1. So there were two other projects that were from Cisco and Mozilla at that time that were also aiming to achieve a highly competitive royalty-free codec, and those were called Thor and Dala. So the idea was to Thor, Dala, and VP10 projects to be combined and to produce one codec that would be part of the OM umbrella, and that would be called AV1. So the work on AV1 started in earnest in early 2016, and then it was worked on between Google, Cisco, Mozilla, Microsoft, and several other companies, Netflix, and so on. And then the bitstream was finalized in 2018, around middle of 2018. That was roughly 5 years after HEVC and VP9. And that achieved at the time about 30% more compactness over VP9, which was what our original target was. And at the time AV1 was released, I think among standardized codecs, this was the best. That we have pretty high confidence that this was the best codec in terms of compactness at the time. And now, like going forward from that, we are trying to get everyone adopted more widely in the industry, and also looking forward to a next generation of an AOM codec in a couple of years' time.
Here's what I've always wanted to know. So how in the world did Google codec engineers and Facebook engineers and Cisco and Mozilla and all these companies come together and first of all, agree, because everybody has their own agendas, right? And their own businesses, their own use cases, even that some are very complementary, some are very different. And then how did you work on this together? I mean, did you literally all get in a room for same room for a certain period of time? Were you meeting like weekly? Were you, what did that look like?
Yeah, so the process was kind of different from the MPEG process. The MPEG process would be like there'd be meetings every 3 months in some exotic place where people would get together for a week, and then they would fight, and then after that go for lunch or dinner together, and so on. But in AOM, we are not doing that. Instead, we are doing weekly calls. But then from time to time, let's say once in 6 months or a year, we would have an in-person event where we would get together, and a lot of the pending items, like pending proposals or pending resolutions of experiments and all, would be discussed and resolved one way or the other over a short period of 2 days or so. So that is how we did. Of course, the processes that we followed at the time were not as structured as an impact process would be, but then it was kind of like a learning experience because that was the first time we were doing it. Now, those of you are familiar with the way the next gen codec from AOM is being developed now. It's much more structured now than what it was at the AV1 time. But that also allowed us to move a lot faster, which was actually good because we wanted to release AV1 within 5 years of VP9, which we were able to do. Now, in terms of working together, of course, when we have proposals from multiple companies in the same area of the code or the same area of the code base, there would be some amount of competition, which is actually not unhealthy. So it was actually good because we pushed each other and actually pushed the other proponents to actually step up their game and actually make things faster or simpler and all of that, which was actually a good thing. The one thing is we are not competing on royalty, so that is actually a big difference. So that was a lot of the politics was out of the game. It was mostly technical discussions and technical reasons was what was driving decisions one way or the other, which was a good thing to have.
How was VP9 chosen, or VP10 ultimately, as the foundation versus Thor and Dala?
So I think at the beginning of the AV1 process, I think we had a VP10 code base which was built off of VP9. So we had the code base was already ready. It was already performing better than VP9. VP9 was, let's say, equivalent to HEVC in coding efficiency, and this was getting maybe 10-15% better than that already. And the Dala was an image codec, so it was not a video codec. So it was the code base for Dala could not have been used right away. And Thor was more for very fast encoding schemes. So when you're operating at the real-time or video conferencing range of the complexity, compactness spectrum, then I think Thor was a good candidate, but it didn't have as much bells and whistles that VP9 code base had to really produce a very high performant VOD codec also. So I think that is why VP9 or starting from VP9 was a very natural choice. So in the early days of the start of the AV1 process, what we did was it was decided that we'll use VP9 with some modifications as a starting point of the code base. So there were some changes that we got together and made related to mostly the transform types and all of that. And that was what we call VP9 Plus. And VP9 Plus was what was used as the starting code base for AV1 development. And then all the other tools that were already there in VP10 and some tools from Thor and some tools from Mozilla were gradually proposed one by one, as well as new tools.
Can you, first of all, just give some sort of an overview of the breadth of tools that were added to AV1, and then let's talk about them.
AV1 is not it's still a hybrid motion compensated video codec, just like any other mainstream codec today. It's not a machine learning based codec or one of the newer paradigms that completely throws away what has been done over the last 20, 30 years. It's still a hybrid motion compensated codec. Now, within that framework, so there you can divide the whole thing up into two or three or maybe four different areas. So one is definitely um, uh, the prediction. So you have to predict. So how well you predict, that's one part. And after predicted, you have the prediction residue and you have to compress it and code it very efficiently. That's like transform and coding of the coefficients. That's another big part of the of a codec. Then after you have after a decoder has reconstructed a frame by doing the inverse quantization, inverse transform, and adding it to the prediction, what you have is a predict as a reconstructed frame, but that reconstructed frame has many artifacts, compression artifacts. So then you need to do a lot of filtering to get rid of the artifacts. And once that filtering processes have been done, then you would want to put them back in your reference buffer pool so that they can be used for subsequent frames as a good predictor. So that's the in-loop filtering part is another big component of that. So yeah, so I think these are the three main areas. So I think one, if you had to focus on a few areas where we think everyone really excelled, I would start off first with the the in-loop filtering pipeline, because I think the in-loop filtering pipeline, everyone is quite a bit more sophisticated than what was there in other codecs at the time. So and also there is this notion of inbuilt super resolution. So I'll talk about that a little bit. So if you think of when a frame is coded, so everyone allowed a mode of operation where a frame could be coded at a lower resolution than the original source. So if the original source is 1080p, maybe we code at lower resolution. And if we do code at lower resolution, then all the predictions that we do, like the interframe prediction, they also need to be predicted from a different resolution frame or a high resolution reference frame. And so the prediction process in everyone is already tuned to actually do this kind of across scale predictions. So we can actually, given any frame and even an interframe, we could actually do pretty well by coding it at lower resolution. Now, once we do that, then we do the transform and all that, and then we get a reconstructed frame, which is at a reduced resolution. And then, so at some point in the in-loop filtering pipeline, we would actually do an upscaling to get it back to the full resolution before we move the frame back to the reference buffer pool so that it can be used for subsequent frames. And at the same time, you can also tap it out and also use it as an output frame. Okay, so now this upsampling process that the in-loop filtering does, on both sides of that upsampling process, there could be some other processing that we do. For instance, if you have coded the video at, let's say, 720p resolution, starting off from 1080p, then your reconstructed video is still 720p. But then your blockiness and blocking artifacts that you see that you have to get rid of would be at the 720p resolution. So your deblocking that you need to run needs to be at the lower resolution. But then after you upscale it, you do another level of processing to again improve the quality and actually get some of the features or basically do super resolving rather than just a plain upscaling. So you can divide up the in-loop filtering process into two main parts. One part is applied at the coded resolution. Then you have the upsampling, and then you have another part that is that is done at the upsample resolution. So that's the overall framework that we have in AV1. Now, among the tools that are used at the coded resolution, we have deblocking that I just mentioned, and then there's another tool called CDEF, and that came it's a joint tool between Cisco and Mozilla. It's called Constrained Directional Enhancement Filter. So it basically figures out the dominant directionality in a small block and then filters along that direction with some components that are orthogonal to them. So it's kind of like a star filter, but oriented based on the dominant direction. So that's CDEF. So you first do deblocking, then CDEF. Then if there is super resolution being used, then you would upsample. If super resolution is not being used, then you wouldn't do it. And then after that, after you have the full resolution bit stream, then you use something called loop restoration. So this loop restoration tools would be something that would involve some kind of learning. So so right now in AV1, the loop restoration tool has a big component which is the Wiener filter. So the Wiener filter is works this way that you look at whatever you have at the input of that process and the source that you want to convey, and then it finds the parameters of a filter that would be learned on a per frame basis and signaled as part of the bit stream. So then the decoder would be using the filter taps that it received from the bit stream and apply the filter, and hopefully the output of that filter will give you a result which is much closer to the source than you originally started out with. Okay, so that's a Wiener filter, and then there's also a guided filter, which also can be used in parallel to that. So for every small block, you can use a combination of either the Wiener filter or a guided filter. Okay, so now this loop restoration tool operates post upsampling, and so there has to be some learning element so that it's no matter how much you reduce resolution by, it should still be able to learn something because you are sending the parameters in a bit stream. So that's why, so that's the entire pipeline. And I think all the tools that we have there are several of the tools here that actually have not been seen in the video codec community at all. Like CDEF is a completely new tool. Then the Wiener filter that we use is a separable Wiener filter, which is much simpler to implement than a non-separable Wiener filter. And also the guided filter is also a tool that has not been used before in any codec in the past. Guided filters have been used for many computer vision applications in the past, but not in a codec scenario. And the way you use it is also very novel. So I think this is the entire in-loop filtering pipeline in AV1, where I think we really push the state of the art in that space through AV1.
Yeah, absolutely. Correct me if I'm wrong, but this is really the first implementation of, I think, what's really machine learning in a codec, right? HEVC did not have any tools that use learning, and I actually don't know about VVC, but
yeah, so the Wiener filter kind of tools were not actually adopted in HEVC. They were adopted. They are now in VVC, but they were not there in HEVC. They were not eventually adopted. So AV1 is a codec in between, and it has Wiener filter kind of tools. But that's also one of the tools that is one of several tools that we have in that pipeline.
Yeah, amazing. Yeah, that's really great. Now, what's another tool? I know that WebRTC is a major application. In fact, it's really interesting that generally a new codec standard is released, and it's always VOD that is the first use case because, of course, you can, time is not as sensitive. You can throw a bunch of compute at it. And, just generally it's easier use case, right? And yet with AV1, we're seeing the opposite. RTC is really the first use case. So tell us about some of the RTC tools that are included.
Well, so I think, that in the RTC use case, one of the major drivers is applications like screen sharing. So I think AV1 is also the first codec where we have screen content coding tools, but they're also part of the main profile. So anybody who implements hardware for decoding of AV1 has to support it. And so if you have a AV1 compliant decoder, then it becomes much more convenient to support like screen content sharing and tools like that. So we have several tools in AV1 inbuilt that actually support screen content sharing. So there is a palette mode where whenever we have screen or even graphics in certain big class of games, you have blocks of an image which has only a few colors. So if it's text, you probably have two colors. Actually, two is actually not true because you have some anti-aliasing being done. So you may have maybe 5, 6 colors. So it's not two is actually never really happens. But even if it is 2, 3, 4, 5, 6 colors, there are modes to say that, okay, only those colors would be like we only have that many colors in a block. And then it's much easier to signal that by sending a mask of which pixel belongs to which color. Rather than actually doing a traditional encoding scheme, which is not really helpful for these very sharp edge-like content that as you see in text or graphics. So palette modes is very useful. Then we have also intra-block copy mode. So intra-block copy mode and palette mode, there's those kind of tools exist in HEVC as in the screen content extensions, but no one actually implemented them in hardware because they are in the part of an extension, which doesn't make sense to. It's more costly to implement those extensions. But everyone, because it's part of the main profile, it's actually much more convenient for people to support screen content like applications with everyone. Now, the interblock copy mode that we have in everyone is the interblock copy is actually not too easy to support in hardware because of various other reasons. But we do have an initial mode that actually works pretty well if you have purely screen content. If you have mixed content, then it's not that useful in the way it's done in everyone, that which are trying to now fix for the next gen codec. But in everyone for pure screen content, that mode works really well. And in addition to the third tool that we have in everyone that supports screen content is the transform types. When you have like text-like content or graphics-like content with sharp edges, then often the traditional transforms, which are really tuned for natural content, don't work very well. Okay, so you have to use transforms. So you can get rid of the transforms and just bypass it with what we call as the identity transform, which means there is no transform at all, and just code the differences or the residues just like a regular block of pixels, and those actually work much better because you have fewer pixels to actually send information for. Because you have a lot of areas that are the same, and then suddenly there are changes, and then everything is the same. So only the change positions you have to signal. And but on the other hand, if you did a transform on that, then the coefficients should be spread out over many different coefficients, and that would be much more inefficient. So I think so. These are the three main tools that support screen content, and as is for RTC use case, this is one of the major applications. So I think we are happy that we were able to keep those tools as part of the main profile.
That's right. Yeah, it's really amazing. Now, the advantages then, obviously, you get bitrate efficiency with these tools. Is there also some computer processing efficiency, or is it mostly bandwidth that?
Well, so yeah, I'd say this is mostly bandwidth. Now, the computational efficiency that's a little tricky because anytime you go from one codec to the next gen, I mean, something has to give, and usually what gives is the computational cost. And what you have seen over multiple generations of codecs is like anytime a codec is released, people usually focus on the VOD use case because they show this much gains at 10% or 20%, 30%, 40% gains over the previous generation codec, but that is assuming a very slow encoder, and which may be possible for VOD use case, but even for VOD, it may be too slow, especially if you consider like service like YouTube, which has like so many millions of videos being uploaded every hour, every day. For Netflix, and where you have a curated few like that amount of content is fewer, it may still be possible, but still encoding complexity is a problem. Now, when you go to the real-time use case, then it's a much bigger problem. So I think in that case, I think the codec industry the codec community as a whole needs to do a better job in actually really reducing the time between the release of a new codec specification and the time when it becomes ready for use in a real-time scenario. So typically there is a lot of engineering resource that needs to be put into that codec, starting from a very heavyweight encoder to actually get it to a stage where you can actually use it in a real-time video conferencing scenario.
Yeah, it's very interesting what you just said, because the desired state for almost all of the services and video platforms is one codec to rule them all, rule the world, to use across. And, you're right. If you are a SVOD service, then that's maybe more possible because you're only talking file based. You have a relatively small number of files. If your content value is high, you probably can afford to put compute cycles behind, behind what it's going to take to do a very high quality and very efficient encode. However, for the rest of us that operate platforms that need to service a wide variety of use cases, what I just heard you say is what we all know is that we're in a multi-codec world. We're in a multi-codec world. Most people look at it purely from a playback perspective, but I heard a different angle in what you're saying. What you're saying is that maybe in time, perhaps there will literally be a codec that is built almost solely for live, for example, has a very specific set of characteristics, performance characteristics. And in that case, if I'm operating across a wide variety of use cases, I may have that codec deployed for my RTC, something else for, yeah.
Yeah.
So
and usually all platforms support multiple codecs anyway. I think
they
that,
do. Exactly.
yeah. Even chipsets, it's if you assume that two codecs will not be used simultaneously, the entire, I mean, all the regular frame handling, all of those things can be shared. So just
well, interesting. Okay, so we said we were going to talk about 3 tools. What's the third one?
Yeah, the third one I wanted to, it's actually not one tool, it's actually a collection of several tools. I think just similar to the in-loop filtering, I didn't talk about just one tool, I talked about an entire area of the code base, of the codec. So similarly for the prediction side, I think everyone went a little bit too overboard to be honest, with a number of prediction modes that we support. And so I think one of the areas that we focused on particularly well is on the compound modes. So compound predictions are where you combine 2 different predictors to create a separate predictor. So let's say so typically you can have a forward predictor and a backward predictor and you average them. That's the simplest form of compound predictor. But in AV1, you could actually combine them in multiple ways. You could combine them based on how close the pixels are. So that's one mode. You could combine them based on the distances of the references of each of the 2 references to the current frame. So you could combine them that way. You could also combine them using wedge. So let's say you can say that if you consider a block where there's a straight line wedge going through it, so maybe on one side of the wedge, you're going to use one of the predictors, and the other side of the wedge, you would be using another predictor with some blending in between along that edge. So that's the wedge mode. And so that's a set of compound inter modes, how we combine 2 inter modes. Then we also have a combination of inter and intra. So for instance, in the wedge case, we could say, okay, one side of the wedge would be an intra predictor, and the other side of the wedge would be an inter predictor. And then with some blending in between. So that's another intra wedge predictor. And then you could also have intra smooth predictor, which is basically saying that you gradually, if you're predicting a block, then from the intra boundaries, you gradually blend the weight so that near the edges of that block, near the intra edges, you're going to weight the intra more. But then as you go further away from the edges, then you start weighing the inter more. And it proceeds along the direction of the prediction. So there are several intra modes that we have there. So I think this entire area of compound prediction, we have many different ways of doing it. And actually they bring each of those separately bring small gains, but if you put them as part of a package, you have a substantial gain. Okay, so that's the prediction tools, but these are also like from AV1, they were sort of like foot in the door in some of these, or actually we're pushing the hardware to do certain things that they were not doing before. But now I think once the hardware, the die is cast, now if they are able to process intra in a better way, then that also helps us on the future codec by improving those tools and having much better prediction modes that use the same infrastructure. So that was one of the benefits. So it does have good coding gain, but it also sets the standard for the industry going forward.
Yeah, amazing, amazing. Well, thank you for highlighting that. Something that comes to mind. I always want to be practical to the audience, to the listeners, and I know that everyone who listens is really going to appreciate the history that you provided and the information. But how would somebody? There's some new tools. There's like any new codec standard, you really need to get under the hood to really exploit. My observation, even as only a semi-technical person, is that sometimes decisions are made a little bit too rapidly about whether a new standard is effective or is not in a use case, because maybe they just didn't take the time to really get under the hood and really learn and to really explore, how to correctly configure and set up and operate. And so how would somebody who's listening and saying, yes, I know AV1 is coming, I clearly can feel the momentum, we're starting to think about it, I need to just get my hands and start learning how all these tools work in my environment. What's your expert guidance, as to how to get up to speed on AV1 as an encoding engineer, as someone who's working directly with the codec?
Yeah, so when everyone was finalized in 2018, so I think there was because we had working on a very tight schedule at the time when everyone was being worked on, we didn't spend too much time on the encoder side to making it faster. So because we are just trying to hit the deadline of 2018. Yeah, so when everyone was first finalized, of course, there is a huge camp of anti-everyone folks that took the software and then met some tests and found it was 1,000 times slower than what a corresponding HEVC software would be. And that was probably true for maybe about a month, but within a month it became that 1,000 times became maybe 100 times. Which is still unusable, but still it was much worse than. But the talking point would stick to many people. Say, "Oh, it's 1,000 times slower." Then what's the point? But then over the next 6 months, it became fast enough that we could actually convince YouTube to start using it, and YouTube would not use it unless the complexity is within check or within limits. So then everyone started being more useful, but the initial impressions people had. Unfortunately stuck with some people. So often what I would like, if someone really wants to explore a new codec, whether it's AV1 or EVC or VVC or anything that they want to explore, I think of course you have to look at the software and run it. But then whenever you have difficulty and you're seeing that the results are not matching what you were expecting or what the proponents have been telling you should get, the best thing is to actually get in touch with the actual people who are developing the software to see what am I doing wrong. So I have seen lots of tests after AV1, more after VP9 was released, but also after AV1, that showed comparisons between AV1 and let's say VVC or JVET and those HM softwares, because they used certain parameters that are completely wrong. So if you use parameters that are wrong for AV1, of course, you will be getting really horrible results. So they'll be using parameters which would turn off all out of order encoding inadvertently, and then that would show like 30% worse than HM, which is obviously not the right thing to do. But at that time, I would say just get in touch with us to see and send us your command line, and we can see what we're doing wrong and all that. And, and of course, now I think 5 years after everyone, or 4 years after everyone has been released, the documentation and all is much better now in the code base and all that. So I think the software itself will have a lot more information.
Yeah. Yeah, that's really great. And, I don't know if you feel comfortable. I don't know if we'll put your email address in the show notes, but anyway, I know you're accessible on LinkedIn. So I think that's a really good suggestion is, when you're dealing with a new standard, get in touch with somebody who worked on it. My experience is, and it doesn't matter if it's in the AOM, with AV1 or, I've worked around the MPEG standards body for a long time. everyone's happy to help. Everybody wants to, because we all have a vested interest, right? We want to see what we worked on succeed. And if there's misinformation, or if we can help guide people in the right path, we want to do that. So yeah, that's fabulous. Well, Debargha, thank you so much. This has been an amazing discussion, and I am quite confident you're going to be back, and we will talk again. We'll find another interesting angle, and really appreciate your time. So thank you.
Yeah, thanks, Mark, for having me. And I really enjoyed my time here also.
Yes, absolutely. And thank you to the listeners. Thank you for listening.